Hi, this video is to help you through the activity on radioactivity. First, let's remember what the anatomy of an atom looks like. Remember that there is a nucleus that contains protons and neutrons, surrounded by an electron cloud. We're going to be focusing on the nucleus today as we talk about radioactivity, because radioactivity comes from the nucleus and interacts with the nucleus. In the next image, I'm going to show just the nucleus in some cartoons of nuclear reactions. Here are my cartoons. I'm showing two different kinds of nuclear reactions here. Both of them have reactants on the left-hand side and products on the right-hand side. In the first kind of nuclear reaction, an unstable nucleus decays or breaks down to give a different nucleus and a radioactive particle or a radiation particle. This is called emission because when the unstable nucleus decays or breaks down, it emits this particle of radiation. Or it's sometimes called decay or disintegration because the larger nucleus can decay into a different nucleus, usually smaller, but not always. So one kind of nuclear reaction is called emission or decay, and those two terms are used interchangeably. The other kind of nuclear reaction is when a nucleus and a particle are combined to make a different nucleus. The feature of a bombardment is that you take the nucleus and add a new particle to it. Sometimes this particle will stick to the nucleus and make a larger nucleus, and sometimes the particle will hit the nucleus and break it apart into different sized pieces. The particle here is actually taken and basically slammed into the nucleus at very high speeds. And we're bombarding the nucleus with these particles. So that's why it's called a bombardment. In the rest of the activity, we're going to be using these terms. So make sure that they make sense to you. Emission or decay is taking one nucleus and making new particles. And bombardment is taking a nucleus and adding a new particle to make either a different nucleus or two other particles. So these are cartoon versions of nuclear reactions, and in a moment we're going to look at the actual isotope symbols that are used to represent these types of reactions. First, let's talk about those symbols that represent the particles that are either emitted or used for bombardment. This is a table showing you the types of radiation or the particles that are emitted from nuclei. In this table, the particles are listed here, the charge of the particle, and the mass number. So I'll note that when we're writing these symbols, for some of the particles there are two different symbols that are used interchangeably, and the charge is not indicated on the symbol like it is on a regular isotope symbol. So let's look at some examples. The alpha particle is represented either by a Greek letter alpha or it's the same as the isotope symbol for a helium nucleus with two neutrons. And that's because the alpha particle is a helium nucleus with a mass number of 4. So notice that mass number here comes from there. It also has two protons because it's a helium nucleus. And so the nucleus has a +2 charge. But we're not really talking about the whole atom here. We're just referring to the nucleus. And so the charges are never indicated on these symbols. A beta particle is represented either by a Greek symbol for beta or this symbol here. And this is similar to an isotope symbol, but it's technically not an isotope symbol because it is an electron, and the electron has no mass, which is why it's 0 here. But it doesn't actually have a -1 proton. It does have a -1 charge, but this symbol is not indicating the charge. It's actually representing a change that will happen in the nucleus, and it shouldn't be taken literally. But this is a symbol that we use, and you'll see how to apply this later. A gamma is written as a Greek letter gamma, and it has no charge and no mass, so it's completely weightless and it doesn't have any protons or neutrons. It's just pure energy. A positron is also referred to as an anti-electron. It's kind of like the antiparticle. It is the antiparticle to an electron. But what you should know about this is that it has, again, no mass, but it has a number 1 here. So again, this shouldn't be taken literally for either the positron or the electron, because if it had 1 proton, you would expect that it had 1 neutron. So this is not technically 1 proton, but it does represent a change that's going to happen in the nucleus when we apply it to a nuclear reaction. So you'll see an example of that in a moment. And the neutron is literally a neutron. So this symbol can be taken literally. It has 0 protons, but it does have 1 neutron, and so it has a mass number of 1. These are 5 particles that you should be familiar with. The positron is something that's really only used in high energy physics labs or talked about in context of physics in the universe. But you'll see the rest of these 4 particles in a medical setting, and we'll discuss that in a moment. So now I'd like to show you a nuclear decay equation. And you can tell that this is a decay equation or an emission equation because you start with 1 particle over here and you get 2 particles over here. And hopefully you can see what kind of emission this is. The kind of emission is defined by the type of radiation that's produced. And this is an alpha particle. So this decay equation is showing you the alpha emission or alpha decay of uranium-238. Now, what I'd like you to notice is that the number of protons over here, 92, is the same number of protons that are going to be on the product side over here. So on the reactant side, we have 92 protons in uranium, and we conserve the number of protons in the products. They're just not all in the same particle. So we can kind of treat this arrow as an equal sign and do a little bit of algebra to figure out how many protons and neutrons are on either side. And if the equation is balanced, then they should match. And all of these equations should be balanced. The next chart on your activity is to help you keep track of the number of protons, neutrons, and the total mass on reactants and products of this particular equation. So let's go ahead. We already said that there are a total of 92 protons in the reactant side, and we can see that there are also 92 protons on the product side because 90 plus 2 is 92. So that number is conserved. Now let's jump down here to the total mass number because that's the easiest thing to see next. The total mass number on the reactant side is 238, so we'll put that in this box. And now we can see the product side has 234 plus 4, which is still 238. So the total mass is also conserved from the products, or from the reactants to the products. And now we can get the number of total neutrons from subtracting the total protons from the total mass number on either side. And you'll see that those should also be conserved. We can use this principle, the fact that the numbers are overall conserved from the reactants to the products, to solve problems like the one that's on the next page. This is showing that an iodine-131 nucleus is changing and giving you this particle. So think to yourself and decide whether this is a decay reaction or a bombardment. Hopefully, you can see that it is a decay reaction because we're taking 1 nucleus and converting it into 2 different particles. And we're going to solve for this mystery particle that's going to come out when this particular particle is released. This is beta emission because this is a beta particle. To solve for the nucleus that's produced when iodine-131 undergoes beta emission, we simply just need to make these numbers balance from the reactants to the products. So over here we have 53 protons on the reactant side. There has to be a total of 53 on that bottom number on the product side. And since the electron is represented with a -1 here, that must mean that whatever thing is here has to have 54, because 54 minus 1 is 53. Then to write the element symbol, all you need to do is go to the periodic table and find 54. Hopefully you can see that it is xenon. And then we simply need to make the top number balance. And since this is 0, then our new number is still 131. So the answer to solve this problem is xenon 131. And once again, this is a beta emission. It's a good idea to pause the video here and complete the questions on this part of the activity. Then please read through the next part of the activity on radiation uses and dangers. Table 2 in your activity lists 4 of the radiation particles that are used in a medical setting, from lowest energy to highest energy. The lowest energy particles penetrate the body least, and the highest energy particles penetrate the body most. So the energy of the particle is related to how far it will go through your body. Something like an alpha particle can be blocked by the skin, and so it doesn't go into your body at all. And that's represented by this figure, showing that the alpha particle stops at your skin. The beta particle penetrates just slightly into the skin, so it can penetrate slightly into your tissues, but not very far. So the beta particle goes through your skin and just penetrates your tissues barely. An X-ray, as you might know from your experience getting an X-ray taken yourself, is penetrating. It can go through the soft tissues in your body, and it's only blocked by the bones. And gamma rays are the highest energy radiation that we're going to talk about, and gamma rays can go all the way through your body, including your bone tissue. The only way to stop a gamma ray is with some heavy metal material like lead. And because lead is so good at blocking nuclear particles, lead is often used in a medical setting in the form of a lead blanket to block any stray radiation particles so that the patient is not overexposed to radiation. In your daily life, you are exposed to radiation all the time. Radiation comes from the atmosphere, and it also comes from the products that we use. A normal exposure of radiation is about 1 to 10 millisieverts, or up to 0.01 sieverts per year. The normal exposure comes from many sources. So about 50% of radiation that you're exposed to comes from what we call background radiation, radiation from the atmosphere, essentially. About 48% of the average person's radiation exposure comes from medical treatments. 2% comes from consumer products like televisions, smoke detectors, and things like that. And then about 0.1% comes from the occupation. And so someone like a radiation technician in a hospital might have a little bit higher occupational radiation exposure than most people. But this radiation exposure in the hospital is carefully monitored for any employees. And you'll see that any employee that works with radiation on a regular basis will wear a radiation badge, which detects the amount of radiation they're exposed to. So they'll wear the badge every day, the same badge, and it will turn a color if they are exposed to too much radiation. And they'll know that they should not be exposed anymore, otherwise they could get sick. Now this table on your activity lists the exposure that's higher than normal and what symptoms that a patient or a person might see. So you can be exposed to up to 0.2 sieverts of radiation without any symptoms. And this table basically lists all of the symptoms up to the point where it's a lethal dose for about 50% of people. So check out this information, read the information that's provided for you in the activity, and then try to answer the questions that follow. Just one more point about medical applications for radioisotopes. There are 2 major applications in a hospital setting for the use of radioisotopes. One is treatment and the other is diagnosis. Treatment means the treatment of disease. So in the case that radiation or radioisotopes are being used to treat disease, the patient already has the disease. And the most common use for radiation therapy is in the treatment of cancer. For example, a brain tumor. When a patient has a tumor, they're receiving radiation treatment in order to kill the cancer cells or the tumor cells. In this application, it's very important to deliver a lethal dose of radiation to the cells in the tumor, and yet try to minimize the exposure to the rest of the patient because you want to kill the cancer cells, but you don't want to kill the patient. In this case, we use short, intense doses of radiation, and we usually use high energy radiation like gamma rays. Once again, the object of this treatment, or the object of the game in this case, is to kill the cells but not harm the patient. So intense doses are necessary to kill the cells, and short so that we limit the radiation exposure of the patient. On the other hand, diagnosis is just to see if someone has a disease or an issue. So in this case, we're just trying to see potential damage, and we certainly don't want to cause any damage, especially in the case of a healthy patient. And so in the case of diagnosis, you want to use the lowest dose possible, and you want to use lower energy radiation. X-rays are a common example of radiation that are used for diagnosis, but of course you want to limit the patient's exposure using lead blankets or any other protective material that will block the X-rays from penetrating the tissue anywhere except for where the image is being taken. Another application for radioisotopes in imaging is for imaging specific tissues. For example, here's a thyroid image. This image is produced by giving radioactive isotopes to the patient in the form of a suspension. So they swallow radioactive iodine, essentially, and because the thyroid accumulates iodine, the radioactive iodine goes right to the thyroid. And then you just need to put a film in front of a person's body, and the radiation comes out of their thyroid through their skin and hits the film and will give you an image that looks something like this. So these are the thyroids in this thyroid image. Once again, you want to make sure in this case that you're not damaging tissue. And so we use very low levels of radiation, but you do need the radiation to penetrate tissue. And so alpha particles are not very useful for this sort of application. Beta particles are, though. So most of the time, the radioactive isotopes that are administered for images like this are beta particle emitters. I mentioned sieverts as a unit to measure exposure to radiation. The unit used to measure the radioactivity of a substance is a curie, and it's represented by a capital CI. 1 curie is equal to 3.7 times 10 to the 10th disintegrations or decays per second. In other words, it's the number of radioactive particles that are emitted per second. And this is a metric unit, and just like in any metric unit, one of the base units equals 1,000 of the milliunits, and one of the base unit is 1 million of the micro units. There are some unit conversion problems on this page of the activity, which you should practice now. On the next page of your activity, there's a table that lists half-lives of radioisotopes. A half-life is the time period that it takes for half of the activity of a radioactive material to disintegrate. So after one half-life, only half of the radiation is still present. This table lists many radioisotopes and their isotope symbol. In the isotope symbol, the number of protons is not listed because you can infer that from the periodic table. So you know that hydrogen is 1, carbon is 6, and so on. What I'd like you to notice is that this table is divided into 2 sections. On the top are the naturally occurring radioisotopes. These are the isotopes that you would find if you drilled down in the Earth's crust and took a sample. You would find some of these things. They're the isotopes that are left over from nuclear reactions in stars and from the Big Bang. Notice that they have very long half-lives. All of these half-lives are more than a year. On the bottom part of this table are listed the radioisotopes that are used in medicine. These radioisotopes are often produced in a laboratory, and they're usually produced by either decaying a larger nucleus or by bombarding a nucleus with radioactive particles to produce these specific nuclei. Notice that the half-lives of these isotopes are much shorter than the naturally occurring isotopes. And these isotopes are chosen to be used in medical setting for a reason, and it's because they have short half-lives. It would be a bad idea to use radium in a medical setting, because if you swallow radium and the radium, it stays in your body, the half-life is really long. And so the whole entire time that the radium is in your body, it will be exposing you to radiation for this basically a really long time. On the other hand, if you swallow some phosphorus 32 and it never leaves your body, it will only be radioactive for a few days. So its half-life is 14.3 days, which means it would decay very, very quickly compared to something like radium. When we're using radiation in a medical setting, a lot of the times our goals are going to be to limit the dose our patients are receiving. And so it's a good idea to use things that have short half-lives so that we can view the radiation from outside their bodies and then it goes away so that they're not exposed to radiation for a long period of time. The last thing I want to discuss is problem number 2, which asks you a question about half-lives. This question gives you the half-life of iodine-131 and a dose with an activity of 200 microcuries. And they ask you how much would remain after 8, 16, and 32 days. One way to solve this problem is using a formula for half-life. But there is a conceptual way that will allow you to solve this problem without having to memorize anything. If you know that you start with 200 microcuries, then write that down. You're starting at 200 microcuries, and this is at time 0 or 0 days. And then ask yourself, after one half-life, how much would I have left and what is the time? So after one half-life, you would be at 8 days and you would have half of your original starting material left. So you would have gone from 200 microcuries to 100 microcuries. Please note that there is a decimal here, so I should have put a decimal in both of these numbers. So there are 3 significant figures. So that would answer my question for 8 days. Now let's go on. If after 8 days I have this, then what happens after the second half-life? After the second half-life, I would be 8 days more, which would be 16 days, and I would have half of this at that time. So now I have 50 microcuries of radiation or radioactive activity at 16 days. And then to answer the 32 days question, I would go through one more half-life, the third half-life, not there yet, and then another half-life, each time dividing the previous amount by 2. So at 32 days, I would end up having 12.5 microcuries of radioactivity. Please complete the activity and the check for understanding for the best results in understanding this material. And don't forget to do your textbook problems and your textbook reading.